Much. Hello everyone, good afternoon. And welcome to the session on smart searching through trillion research papers using Apache Spark ML. Right. So before we begin with the session, please allow me to introduce myself. My name is Himanshu Gupta and I'm working with Knoldus as a lead consultant engineering, and I work on reactive and streaming fast data solutions by leveraging Spark and Scala ecosystem from past 4 years. Now let's begin with the session. So the agenda for this session will be, first we'll be looking at the requirement, like why do we need to search through a million or trillion research papers using some sort of a ML capability. Then we will look at the challenges that come up while building such an application or a platform. Then we will look at the solution that we came up and how we solve this problem. And in the last, we will look at the future work that we are planning to do or add to this platform. So let's first begin with the requirement. So for any kind of industry, the first and the foremost requirement is to make decisions better, or to make better decisions much faster, right? For example, if we talk about automotive industry, then for them it takes about 2 to 5 years and $1 billion to bring a car from the concept phase to the sales floor, right? Because it takes a lot of effort, research and development part to do so. Similar is the case with the pharmaceutical companies. For them, it's even more tougher and a much more tiring process, because it takes about 10 to 12 years and about $2.5 billion for them to bring a new drug into the market and get it approved, right? Now, now adding to those problems, there is no guarantee for that product to be successful. For example, in June 2018, Tata Motors was able to produce only 1 unit of Nano, which is the world's cheapest family car. Or if we take example of, in case of pharmaceutical companies, then for a few diseases, it's the success rate of any new drug or medicine being approved is less than 20%. So even after spending so much time and spending so much money on research and development of new products, there is very less chances of it being successful. Now, what can be the solution for this thing? The best solution is to leverage the work which is already being done, right? So, using that philosophy, 60% of the cars in India, those use common engines or the common platform to be built upon, right? Because it saves a lot of money to build any product from scratch, right? They can reuse the components. Also, the pharmaceutical companies partner with research organizations and academic institutes to reduce their cost of R&D up to 30%. So, because it might happen that those research organization institutes might have done research already, or might have done the work which they are trying to do or planning to do, right? Now, what is the challenge that come up while leveraging the work already done? The challenge is it is quite difficult. The reason for that is the R&D data is extremely complex to understand, right? Because because each and every research work have a very specific aim, which can overlap with other research work or not, right? So we have to find out what that research work is trying to prove and whether it is being already done or not. The next thing is the test environment in which the scientists and the researchers work is different from the actual environment, right? Because they assume or ignore a lot of factors which are present in the actual world. So it becomes quite difficult for understanding, like for taking into account all those factors when building a new product. The next thing is facts are scattered over different research work, right? So there are multiple research papers and articles which are trying to solve the same problem, and they might contain the different facts about that work already being done, right? So the challenge is how to collate all the information from different research papers and articles into one place and allow the user or to help the user to answer their query easily. Our solution. So our solution was to build a platform where all the work done, that is the research papers and the articles, are collated, that is present at one place. It also allows easy access to the relevant research work. That is, it showcases or it like presents only the research papers or the articles which are relevant to a user query. And the last thing, it should be able to discover new fields or the concepts which are different from the existing ones. Now, what these fields and concepts are, we will see in the further slides. Design philosophy. So the design philosophy of this platform is quite simple. It contains three major components. The first component is extracting the content, right? So I'll be elaborating all these components in the further slides, but the extracting content means that we extract out the data from those research papers and the articles. The next phase is to analyze that data, right? That is applying the Spark ML and different algorithms over it so that we can identify the concepts or the facts or extract out those things from the research papers. And the last thing is storing the facts. That is matching up the documents or the research papers that we have along with the concepts identified, right? So let's begin with the step one, which is the extracting the content. So extracting content from research papers or articles is a time-consuming and a tiring process if done manually, because it requires the expertise of SMEs. SMEs are subject matter experts. So for example, like if we want to extract out the important information from a paper on manufacturing process, right, for automotive industry, then we would need the help of metallurgists, right, and some other experts as well. So extracting information requires the expertise of these subject matter experts. However, if we can extract out that information through systems, then this process can become a lot more fast and cost efficient. Also, systems systems extract content from the research papers articles and store them into a database from where it can be explored for further exploration or analysis. Now, let's take a look at the extraction process. So the first step of the process is to read the documents or the articles from S3 or HDFS or some sort of a network file system, right, where it is already stored in a distributed format. Then we index the content. By indexing means that we distribute it into few major components. The three major components are title, because the title, which specifies the aim. The second one is structure, basically exploring the different sections of the paper or the article. For example, like its abstract, different sections, introduction, and other things. And the last thing is the special objects, like tables and the figures, which contains the factual data or the measurements in any research paper or an article. So these are the three major indexes that we have in that. Next step is to enrich that data. It means that make the data suitable for the systems to understand, right? In our case, it was just an M by N matrix, where M was the number of the documents that we have, and N is the number of unique words that we identify from that content. And in the last, we save that data into a database for being processed. So this is how our data looks like. So every document here represents a row. It's a structured data, right? And every word is a column for us. And the values are the count of that particular word in that document. So the data is the data that we get after extracting the content is quite simple. Let's move on to the step 2, which is the analyzing the content part. Now this part is divided into two phases. The first phase is applying the Spark ML so that we can identify the concepts in it. In the first phase, we use the Spark LDA, which is a kind of a unsupervised learning machine learning algorithm, right? So we just apply the Spark LDA over our content or the feature vectors that we get and save the results in the database, right? So this is how our content or the analyzed concepts look like. Here, every word is a row in the structure, and every topic is the concept that is identified from that research paper or the article. Now, every word has some significance, or for example, like in terms of computer, we say term weight in that particular concept, right? and it varies from 0 to 1. Okay. Now, it's not necessary that the above words are the final clusters or the final concepts that we have that is being identified. Why? Because every concept can contain, or every word belongs to a cluster even with a probability of 0.001%, right? But in order to identify like which words are highly significant in a particular concept or not, that is what we want to identify. So for this, we apply the second phase of analyzing the content. So in this phase, we identify the clusters or the core, or basically the concepts that we say. For this, we first measure the dispersion, that is, calculate the sigma of the term weights. Sigma is just a value to identify like how much significant that word is to that, or related that word is to that cluster or the topic is, right? Next, we pick the top words. So we pick the top words using the 3 sigma rule that we have, which actually captures the 99.7% of the values present in that cluster, right? Or basically those words which are highly significant to that. After that, we find similar words, that is the words in the cluster with high cosine similarity. So the cosine similarity tells us how much closely related these words are to each other, right? And the next step is to find the co-occurrence. In the co-occurrence part, we actually check the PMI values, which is the point-wise mutual index information, or just the information, which tells us like what is the probability of 2 words like New York or United Kingdom being occurring together if they are present in a document, right? So we identify those, we calculate that value, and the last we calculate few metrics, for example like cohesiveness, distinctiveness, and sellout coefficient. Now these metrics are important in order to identify the quality of the clusters that we get, right? Because we want to check how significant or relevant our clusters or concepts are once they're identified. The next or the last step is to check whether the concept that we got from the research papers or the articles is a new concept or just a drift from an existing concept, right? If it's a new concept, then we give it an ID or a name and save it into the database. Otherwise, if it's just a slight drift, then we leave it. Now, now this is how a particular concept or a cluster looks like, right? So this cluster tells us that the words related to the disease called tuberculosis contains word like illness, health, or maybe few technical terms like microbacterium and those kind of words. So any research paper or an article related to this concept, which is the tuberculosis, has a very high probability of containing these words, right? So the cluster of words from the research papers on tuberculosis looks something like this. Now let's look at the last phase or the last component of the platform. The last phase is storing that facts. In this phase, we actually index the documents which we use to identify the concepts, because till now we have been able to identify just the concepts or the clusters which exist, right? For example, like diseases and few processes, and that's it. But in order to search or in order to make those documents searchable, we have to bind them with the clusters that we have got, right? So in this process, what we do is we convert our clusters into a feature vector. A feature vector is nothing but a 1 by n matrix where we just give it an ID and say, okay, these are the words which exist in that cluster, and match it with the words present in our documents. And in matching process, we actually check their cosine similarity. If the match is greater than 90%, then it's a very high possibility that that document belongs to that cluster. But if the probability or the match is less than 75%, then we take the help of subject matter experts. That is, we send that document for manual inspection, right? Because no algorithm or no process is perfect, but in order to actually index them, we take manual help as well. And in the last, we index that document as well. And for indexing, what we do is we just give it an ID, keep the starting point of the document from where the concept actually starts, and the length, like till where it is. Now, this is how our index of documents and related clusters looks like. It contains the document ID and the content and the cluster ID as well. The cluster terms which exist in that cluster, and the similarity portion. And the last, we have the location of that concept present in that document. Now, with the help of this indexing, anyone can search those documents on the basis of a simple query. For example, like select star from the facts or this table, where the core terms like metallurgy exist, which will like bring or pop up all the documents and the related articles related to the metallurgy. Now, we can even refine this search further on the basis of the similarity as well, right? For example, like we want the documents which are highly, which have the probability of the match or which greater than 90%, right? And we can even change our query as well for searching those documents. So this is how our platform extracts the content and helps the user to search through the relevant documents that are present using some of the ML techniques that are present in Apache Spark. Now, the future work that we are planning to work on. So the first feature that we are planning to work on is a semantic search, which will allow the user to search for the documents using a semantic query. For example, how can we separate gold from mercury, right? So if anyone is looking for information regarding this query, then it will bring all the documents or the articles related to just this query. So instead of typing in a SQL query or a SQL query there, right, the user will be able to type in their queries in a much more natural form, okay, and get the results. For this, we are taking help of the Elasticsearch or the Solar, which have much better search capabilities than an SQL table. And the last thing is building a quality workbench, right? This quality workbench will measure the relevance of the search that is being found out, right? So a lot of search engines today tells us how relevant the documents that we have got is related to your query. And not only it will help us help the user understand how much better the search engine is, but also it will help us in tuning the ML algorithms that we are applying for this platform, right? Now, with that, I wind up my session. So any questions related to this? Yeah.
Inside the Hadoop or Spark or remember, and then load it to Solar or Elastic. Maybe I think we need kind of.
Sorry.
I think we need kind of standard to build indexes for Elastic, Solar, and Spark. Are you doing something like that? We can build a Solar index inside Spark and load it, or any standard for clustering and indexing documents?
So right now we have just started this work, right? And we are looking at what can be the probable index that can be applied into Elasticsearch or the Solar, which helps us in better search capability over those documents. Of course, we cannot apply those indexes over the document itself, right? Because in that case, the index will become too huge and difficult to manage. But we are trying to find out what can be the probable way to do that. Maybe we can also add the similarity part as well, which can help us in better searching of those documents.
Thanks.
Hi, can you share some statistics about what platform did you use, and any configuration, or because of the volume, and was it on cloud or was it in premises, or something like any performance metrics which you can share?
Yeah, sure. So I do have those statistics. So right now I don't have those statistics, but as far as the performance is concerned, so we were able to index about like 500,000 documents using this approach. Since the whole process was done on cloud, that is the AWS, right? And we used about like 20 node cluster of Spark for doing this, and 5 node like Cassandra cluster there for running this platform. But it took us, like initially it took us a long time to understand how the Spark LDA actually works, and then we actually optimized it, and we took it over run over within an hour instead of running it over a whole day initially. So it took us a time to actually tune the various parameters which Spark LDA takes in, like number of clusters, or the number of topics to be discovered, and what parameters to use there.
I have two questions. Could you please go back to your slide of word cloud output? Because you mentioned about use case of new drug development, and I see like related word to this disease, and I don't know what can I really learn. I'm a little bit confused. Like for the new drug development, for instance, what can I learn out of this output? Could you maybe?
Yeah, sure. So there are a lot of like organizations or institutes which are actively working on existing or new diseases, right? And they in their research paper, if they find anything new, they just publish it on that part, right? So for example, if any pharmaceutical company is developing a new medicine on tuberculosis, then the work done by that institute, which is already published, they can use that for improving their like medicine or the drug. Now, when anyone is trying to understand the behavior of the tuberculosis disease, right? Like what bacteria is there. So I'm not well versed with biology a lot here, but when they're trying to understand the behavior of this disease, then they would definitely need to know what work has already been done, and because that saves a lot of time for them to like just go through all the research papers manually or the articles, and then start working on it, because it might happen that the work there which they are trying to do is already done by some other organization or the institute.
But if I remember correctly, for the pre-processing step, you are kind of checking the frequency, and it's very hard to detect like newly published paper if not many people mention about. I think it would be hard to detect for like really innovative solution recently published. Do you have any kind of solution to detect it?
Yeah. So one of the like upcoming features that we are trying to add is, instead of like developing our model in a batch way, we can do it in a streaming way as well, right? Because that will help us to to add new articles or the new work done into our model, which we will keep on like evolving and present the new work done to the users.
Final question, sorry.
Yeah.
Is there any attempt to validate the results? Like maybe you have golden data to compare and so on?
Yeah, so initially we took the help of SMEs, which are the subject matter experts, to check whether like how relevant our queries or our search platform is. And they, on the basis of their feedback of different concepts that we have, we actually fed that back into our model. So it's kind of a learning model, right, which keeps on improving. And also to automate this process, we are trying to develop a quality workbench here, right, which will tell us how good our platform is. So if you remember that in step 2, we collected few matrices, which are the cohesiveness, distinctiveness, and the sellout coefficient, which will tell us how good our model is, right? So we do that for every new concept that we find.
In this same slide, the blue box with find similar words, you find similar words with cosine by using cosine similarity. So the words are, what is the embedding of the word, how you measure cosine similarity, and whether it's the same cosine similarity over different topics, or it is something like the embedding is specific to the topic or specific to the document for the same word.
Okay, so by finding the similar words, we mean that how similar a word is to other words, right? For example, if I take about example of strong, stronger, and the strongest, they actually mean the same thing in terms of their meaning, but in a document they can be present multiple times in different concept, in different context, right? So what the aim of this step is to find out the similar words and just simply filter them out, so that we can keep just the words which are highly specific or highly specific to our concept there. It also serves one more purpose, which is finding out how similar one word is to that particular concept of the cluster is. So if I take the example of tuberculosis, right, then for example, like if I take word cough, now that is one of the symptoms of the tuberculosis, right? Now most of the research papers or the articles which are written over tuberculosis will contain this word. Now this word will have some similarity with this disease because its occurrence is too much in the papers related to tuberculosis, right? So that step helps us identifying words like this.
So about the very last question that was asked about the similarities, have you considered stemming the words, so like similarities all be categorized as similar? That's the first question I have. And as the follow-up, I want to know, I know that you're gonna dive deeper in the more linguistic aware things later, but at this point, are you doing anything to recognize the relation between small and tiny and this kind of thing, so you would know that this is the concept that we are talking about? I know that when you get the linguistic in place, you would have much more information, but anything out of the box that you guys worked on?
Yes, sure. So after building a very raw form of this platform, we took the help of some of the NLP experts, and they came up that there are two processes that we should apply. First is the stemming, and the second one is the morphing, right? With the help of which we were able to reduce the vocabulary size, because initially with the step 1, the output that we were getting or the values that we were getting was too huge. That matrix was too large to process. But after applying the stemming and the morphology, it got reduced. So yeah, that is part of the platform, but that is something which helps, which we are trying to apply in pre-processing part instead of applying it at the analysis stage.
Great. I think we have time for one more question if there's anything else.
Hi, sorry I joined a bit late, so I might have missed a few slides early on. Just want to ask why this solution is probably better than maybe something you get out of Solr, a search solution with a Solr or Elasticsearch stack. So, like a summary of what things you get. How is this better than what you can maybe
Okay.
implement using Solar or Search?
Yeah. So whenever we talk about any existing framework like Solar or Elasticsearch, then correct me if I got your question correct. So you are trying to ask like how this platform is better than Elasticsearch or the Solar, which helps in better search, right? Okay. So whenever we talk about the any existing technologies like Elasticsearch or the Solar, right, they help us in a better search, right? But they won't be able to help us in identifying new concepts. So, for example, if I take example of any existing search engine based on Elasticsearch or Solar, right, and I try to find out the work on like metals related to or how they react to few gases, right? Then it will start showing me some random research papers or the articles as well, right, which are not relevant to my search. And even though they might contain those words, but they are not relevant to it. So this platform helps in better understanding those, in better understanding or making the search much more relevant to a particular user query using the machine learning capabilities of Spark or any other framework. But we use Spark for that purpose. Okay.
Thank you so much. That's all the time that we have for this session.
Okay.
If you have any more questions, you can probably go talk to him in person, but thank you so much.